Welcome everyone to the Friday Transportation Seminar of the Transportation Research and Education Center, TREC, at Portland State University. So I'm Jennifer Dill, I'm Director of TREC, and I will be introducing and moderating today's seminar. Whoops, sorry, I'm a little rusty at doing this. So our Friday transportation seminars have been a tradition since the year 2000. These seminars are usually held live on the Portland State University's urban campus, located on the ancestral homelands of the Multnomah, Cathlamet, Clackamas, Tumwater, Watlala bands of the Chinook, the Tualatin Kalapuya, and many other indigenous nations of the Columbia River. It is important that we acknowledge that we are here because of the sacrifices forced on the indigenous ancestors of this place, remember these communities, and honor their legacy, lives, and descendants. Due to the COVID-19 pandemic, today's seminar is hosted fully online. Today, I'm very pleased to have two of our outstanding PhD students at Portland State University, Sangwan Lee and Darshan Chauhan, presenting some of the research that they presented I guess only a week ago or so at the annual meeting of the Transportation Research Board in Washington, D.C. So we have two presentations. We are first up will be Sangwan Lee, is a graduate research assistant in the Nohade Toulon School of Urban Studies and Planning at Portland State. He has also served as a teaching assistant at Rutgers University, the State University of New Jersey, and as an assistant research fellow in urban engineering at Chongbuk National University. He is currently a PhD student in urban studies with a focus on regional science. He earned his master's in city and regional planning from Rutgers in 2019 and a master's in urban engineering at Chongbuk University in 2014. He also earned a BS in architecture and urban engineering from the same university in 2012. So he'll be our first speaker. Our second speaker is Darshan Chauhan, and he is a PhD candidate in civil and environmental engineering and a graduate research assistant at Portland State University. His doctoral work with Dr. Avinash Unnikrishnan is on planning and real-time resource allocation in freight logistics systems using robust optimization and reinforcement learning. He is also interested in data analytics and its applications to transportation safety using econometric modeling. He has served as the treasurer of STEP, our Students in Transportation Engineering and Planning, which is PSU's ITE student chapter. And you can see the titles of their presentations on the screen. Before we switch over to them, I want to tell you about some upcoming Friday transportation seminars that you can see listed here. We have a great lineup starting on February 4th with Jamie Volker from UC Davis talking about induced vehicle travel. And then some additional on the 18th, we have a presentation of some other work that was presented at TRB, and we know that not everyone could attend TRB this year, so we are sharing some of that work at these seminars, and then you can see some additional ones scheduled for March. I will also put in another plug for an opportunity for our study abroad program that will be happening this summer, which will focus on sustainable transportation in Denmark and Sweden. And the applications are due January 31st. There is a link on the slide that we will also be putting in the chat if you're interested in learning more about that. And for those of you who might be new to attending our Zoom webinars, we're going to have Because we have two speakers on two different topics today, we will be doing some Q&A at the end of each speaker. We ask that you use the Q&A feature at the bottom of your Zoom screen to type in your questions for Q&A. And I hope we should have time for all of the questions. We have enabled closed captioning, but you must click on the closed caption feature on your control panel to view them. We are recording today's webinar and it will be available on our website later today along with the presentation slides. And if you are tracking professional development hours, it's eligible for 1 hour of continuing ed credit. And with that, whoops, I went too far. I'm going to turn it over to Sangwan. And I'm going to stop sharing. Thank you so much.
Hi, everyone. Thank you so much for joining this seminar. First of all, I'd like to very quickly introduce myself. I'm Sangwan Lee, and I've been doing research mainly on transportation and land use interaction like this study, as well as emerging transportation modes such as autonomous vehicles by using quantitative analysis. Today, I'd like to share a project with Dr. Liming Wang and Aaron Golub in our department. And first, I'm going to present a quick introduction and show the research design and findings, and then discuss the results. And I don't have plenty of time for this presentation, so I'm going to cover important things, and let's get started. Usually, diverse features of homes factor in property values, such as the view of housing and nearby school quality and so on. Also, the proximity to transit station is one of the key factors to determine property values. And the effect of the transit accessibility is called the property value premium of transit. And the premium has changed over time. For example, Dr. Gallo found that the premium varied depending on the transit planning phases. And Dr. Wang and I found that the premium dissipated over time. And on the other hand, COVID has influenced not only public health, but also many aspects of our lives, such as plummeted transit ridership and changed residential location preference toward least populated areas. So we were curious about how COVID impacts the property value premium of transit, given the temporal dynamics of the premium. So we asked whether COVID has significantly impacted the premium of light transit in single-family and multi-family housing market in the Portland region. We believe this paper helps to understand its impact on the real estate market and opens up the discussion of its impact. I'll skip literature review section given the limited time. So the main concerns of research designs are how can we quantify the COVID impact on residential property value? And how can we make causal inference? And how can we estimate unbiased effect as much as we can? So that's why we use the 4-step process. First, we collected and cleaned lipid cell data. The lipid cell data means properties transaction multiple times. In this case, all lipid cells include one before and one after the COVID outbreak to capture the causal inference. And second, we used propensity score matching to find matched treated and control groups that share similar characteristics. Here we used 17 covariates that may impact property value, and it means that the only difference between matched treated and control group is the distance to the nearest light transit max in our paper if it is working properly. Third, we used spatial econometrics to estimate the treatment effect. The treatment effect in this study means the difference between the matched two groups in appreciation rate, which is sale price after the COVID outbreak divided by the before. So the dependent variable was the log transformed appreciation rate, and the key independent variable was obviously the dummy variable of whether an observation is in the matched treated group. We also control the length of time between two transactions to address the seasonality issue. And we also tried to control for covariates that were not perfectly matched in PSM, but balanced diagnostics suggests that there was no need to control for them. I'll go over this shortly. Lastly, we did sensitive test to examine the robustness of the final model. Let me share a little bit more details on the risk design. First, the pre-COVID period was between January 2016 and February 2020. We chose January 2016 because, as I said before, the premium can vary depending on the transit planning phases. And we wanted to rule out the temporal effects. And then also the during COVID period was between March 2020 and May 2021 due to the data limitation. And second, I'd like to show you the broad trend in transit ridership and probabilities in the Portland region. As you can see from the figure on the top, transit ridership significantly decreased after the COVID outbreak, but it seems that there was no significant impact on COVID on the real estate market in the region. And for one more detail, we removed transaction records whose price change between two periods was lower than minus 50% and higher than 50%. We picked this plus minus 50% cutoff because for Portland region, the average year-over-year change only reached around 18% during the peak period between 2006 and 2008 before the financial crisis, and it only reached around negative 50% during the crisis. But there is no consensus of this cutoff. We did sensitive tests for different cutoffs while using the same four-step approach. Now I'm going to present the results of this paper. First, I'm going to show you the balanced diagnostics of PSM to check whether the methodology was working properly. For PSM, as I said before, we used 17 covariates. The covariates on the y-axis include the structural characteristics such as building area and lot area, and locational factors such as distance to downtown, freeway, ramp, streetcar, and bus stops. And also we included neighborhood characteristics such as population density, employment accessibility, and land use diversities, and something like that. So, and for the diagnostics, we used a standardized mean difference in the figure on the left side and the paired t-test in the figure on the right side. First, the results of standardized difference indicate that we found the perfectly matched observations because none of them was above 0.25, and the results of paired t-test confirm this. As you can see in the figure on the right side, none of the p-values was below 0.1, which is marginally significant level. However, since we did not use all factors to impact property value, we cannot say that we conducted a pure random experiment, but given the results, we approximated the random experiment to find causal inference. And this slide shows the matched observation. The two figures on the top show the location of matched observations in the two real estate market, and the red dot means observations in matched treated group, and then blue dot shows those in control group. And more importantly, the figures on the bottom show appreciation rate of matched observations. The red color means the higher appreciation, but the bright yellow indicates lower and negative appreciation rates. So the figures visually show that single-family homes with higher appreciation rates seem to be located near max stations, which is the black dot, but multi-family homes with higher appreciation seem to show the opposite results. So to quantify the effects of COVID on appreciation rate, we used spatial lag and error models. And then we found the spatial error model outperformed the spatial lag model and typical hedonic regression model. And so we interpreted mostly the spatial error model with a plus minus 15% cutoff. So as you can see in the figure, on average, the appreciation would be 1.7% higher if a single family home was within a half mile from the nearest max station compared to otherwise similar control properties. Note that this 1.7% is the additional appreciation single family homes had between before and after the COVID period, not the classic premium of transit. And as you can see, the treatment effects of other cutoffs on the x-axis, all treatment effects were positive. And however, the appreciation rate was 3.2% lower for multi-family homes located in the Raleigh transit service area than otherwise similar homes. Also note that the negative 3.2% premium indicates the lower appreciation multi-family homes near max stations. Max stations had between the two periods and well after max systems were already established, and then supposedly any premium of max had already been reflected in the price. And like single family housing market, all treatment effects across different cutoffs were positive. And now I'm going to discuss the findings. Regarding the single family housing, Richard Florida has recently argued that COVID might lead to a series of changes in short term, but it is unlikely to change long-standing spatial patterns. Extending this argument to our paper, COVID has influenced the transit ridership, but our results suggest that the plummeted transit ridership do not necessarily mean that the transit proximity has lost its appeal in the single-family housing market. Also, some people might have relocated from max accessible multi-family homes to single-family homes, probably because of the concern of max COVID exposure in multi-family homes and demand for yard space during the lockdown. And this may explain the conflicting results between the two markets. And home buyers in single-family housing market may think that this disruption from the COVID pandemic would be short-term. And lastly, a shorter walking time to transportation would remain important because it can provide easy access to the station and lower probability of contacting people on the way to that station. And for the multifamily housing market, households may prefer suburbs over highly populated area because the highly populated area may lead to higher probability of spreading the virus. So multifamily homes near train stations may be considered least favorable because they are generally in the highly populated area. And also the plummeted transit ridership may disrupt the demand for the homes because transit service area generally have a market with multifamily housing demand that is sensitive to proximity to amenities and social services. And this paper obviously has several limitations. For example, we weren't able to include important home characteristics such as the number of beds in proper score matching because of the data limitation. Also, this paper did not capture all dramatic changes led by COVID, such as temporarily closed amenities and unemployment, to quantify the effect. And also, this paper may seem to be immature to have long-term effect of COVID. So we hope to revisit this paper in several years to estimate this. Thank you so much for your interest and attention. And if anyone has any questions, please feel free to ask. And Dr. Wang and I will do our best to answer. And more importantly, feel free to share your thoughts, because this paper is for opening up the discussion on the COVID effect. Thank you so much.
Great. Thank you, Sangwan. I have lots of ideas and comments going through my head, but we do have two questions that came into the Q&A box. And one is pretty specific about your methodology. And that is, what was the logic behind the removal of repeated sales data? There's two questions. So let's start with that one. Why did you remove the repeated sales data? And it may help to maybe explain what repeated sales data are.
Let me clarify the question, because this paper used the repeat sale data, but the question was removal.
Oh, okay.
Yeah,
so maybe there was a misunderstanding. So
yeah.
Could you maybe as
Maybe-
a starting point explain what repeated sales data are?
Yeah. Repeat sale data means that sales transactions multiple times, which means that let me talk in this way. So for the capture the causal inference, in this case before and after the COVID impact, we should have one transaction before the COVID and one sales transaction after the COVID. But this sales transaction has to be the single one observation. That means the repeat sale data. And then I think the question was about the cutoff, plus minus 15% cutoff.
So that was the second part of the
Probably.
question.
Yeah.
So let me share, because not, well, I can't remember if everyone sees it. So the second part of the question is, why did you remove the price change within the 15% cutoff? So maybe explain that.
Yeah. We picked this plus minus 15% cutoff because we believe it is the best one for two regions. Firstly, as I said before, for the Portland area, the average year-over-year change only reached around 80% before the financial crisis, and only reached around negative 15% during crisis. But and also more importantly, the crucial assumptions of the repeat sale analysis is that the innate characteristics of properties should not change throughout the study period to capture only the change in the price change. So since our data source do not have the information on the renovation and remodeling or other improvement to the property, we need to rely on the cutoff to provide a filter of properties with the major improvements between transactions. So we use that the plus minus 15% cutoff. So, but we obviously acknowledge that there's no consensus of this cutoff. So that's why we did the sensitive test for different cutoffs. And then as you see in the figures in the result section, there was marginal difference in the effect size, but overall there is consistent. For example, like single families, consistent, and then positive treatment effect. And for the multi-family housing, there is a consistent and negative treatment effect. So yeah, thank you for the question.
Yeah, so it seems like you decide on a cutoff, but perhaps your findings are pretty consistent
Yes, yes.
Because of that sensitivity analysis.
Yeah,
So
yeah,
the
yeah.
other question here is a little broader, and which is why you chose to focus on proximity to light rail stations instead of other types of transit, such as bus stops.
That's a really good question, and then that is because of my motivation of this research. Because in my case, when I rent a room, I really care about this proximity to transit because I don't drive and something like that. So I need to get some place to by using Max or other kinds of alternate transportation modes. So that's why I'm into this proximity to train station. So it's kind of very personal motivation behind this paper.
I think I would also add, and I'm guessing, Sangwan, that you've read this literature, is that there is the evidence that bus transit, particularly not like fixed or busways, bus rapid transit, but just regular bus service, the evidence that that affects property values is pretty weak or non-existent. And there's just stronger evidence that light rail and other types of rail has an effect on property values. And particularly in Portland, where we do not yet have any real bus rapid transit, which might. Oh, and that is actually my colleague, Dr. Wong has just added that as well. So yeah. We are thinking alike. So with that, we are almost at noon. And so we're going to switch over to our other speaker, but we should have a little bit of time at the end. If people have additional questions for Sangwan, we can probably come back to this. So thank you so much for your presentation. Quite interesting. And now I am going to turn it over to Darshan.
I hope you guys can see the presentation. Perfect. Hi all. Thank you, Sangwan, for an interesting presentation, and thank you, Dr. Dill, for the introduction. Thank you all for attending. This project is a part of the work that I'm doing for my PhD with Dr. Unnikrishnan at the CEE department at Portland State. Before we dive in, I'd like to thank my collaborators on this project, Professor Unnikrishnan and Professor Figliosi from Portland State and Professor Boyles from UT Austin. Also, many thanks to the National Science Foundation and the two university transportation centers for supporting this research. We'll kind of go in reverse order of the title by first talking about emergency services, then talking about coverage reliability, and then we'll go over a basic facility location model for drones that maximizes coverage. Then we'll discuss certain avenues to improve this basic model and how to include them in our decision making. Finally, I'll go over some of the insights that we obtained from modeling and conclude the research with some recommendations. So all emergency departments need to maintain some required level of service, right? These level of service requirements often come as reliability constraints. For example, the NFPA dictates that the US fire departments have at least a 90% response rate in 4 minutes. That is, they need to attend 90%, at least a 90% of the calls that they receive in 4 minutes, right? And there is, apart from that, there is a growing exploration and going away from ground vehicles that have traditional modes of issues in travel time reliability because of congestion, is going towards drones, and they are being field tested as part of federally funded programs, like the Federal Aviation Authority's UAS IPP and UAS Beyond programs. So among the participants of this federal program is the city of Reno in Nevada, that is field testing AED-enabled drones, that is automatic external defibrillators, attached to drones and for tackling out of hospital cardiac events in the area. So the motivation of this study is to apply the same application, but for Portland metro area. Here we do two things differently from the current state of operations by emergency departments. First is we enforce the reliability constraint at a demand point rather than at the facility, right? Why? So that we divert our attention to the end user of this, program. That is by asking the question, is the demand point being reliably covered or not? Rather than asking the question if the facility is performing at a given level of service. This is also helpful in incorporating some equity-based considerations that need to be made in decisions. Right? And the second is that all accessible units within a radius, they respond to this, demand request, so that this improves the probability of timely arrival and therefore survival in case of out-of-hospital cardiac arrests. This is also possible in case of using drones, is because they have a lower operational cost as there is no labor-based less labor-based requirements. So now, how does this look? Let me do this. Yeah. So consider a demand point, and around it is an accessibility radius, which is governed by the service standard. So if it is 4 minutes, this radius will represent 4 minutes of travel time, in the best case scenarios. So we consider all the open facilities in that radius. So if this demand point has an out of hospital cardiac event, all of the open facilities in this radius, they come, they start traveling here with AEDs. We want that the probability that at least one of them arrive is greater than alpha, which is the reliability standard that the agency wants to achieve. Then what we do is we assume independence to make this amenable for modeling. So this is how a basic facility location model would look, is that we want to maximize coverage, and there is a reliability constraint by assuming that independence. So when yj is 0, represents that there is facility not opened at location j. So this we are essentially multiplying by 1, and when yj is 1, it will have the value pij. Similarly, when xi is 0, we are essentially saying that it's less than equal to 1, which is always the case. And when xi is 1, that means the demand point I is reliably covered with standard alpha, right? And we have a total of q drones that we want to locate in this service area. It is of note that this parameter ci represents the coverage importance, right? So it can be a composite metric that includes factors like population and demographics, emergency calls history regarding cardiac events and those kind of things, and other equity considerations that the agency is hoping to achieve, right? So maybe like further away locations have more importance because they need to be, they should have more say in maybe this type of situations. So how are the decisions being affected? Wind speed and directions are one of the major environmental factors that affect the performance of drones. So what we do first is we have this wind speed and direction distributions. We sample it, and for the best case, we assume that the wind direction is aligned to the delivery direction. And for the worst case, we assume that it's against the delivery direction. And then we calculate the average by weighting them, in terms of its alignment with the wind speed distribution, wind directions, right? And then once we get this weighted average, we input that in facility location model, and what we get is the selected locations which are open for drone, operations, and the demand points that would be reliably covered, right? So now that we know how decisions are made and affected, we now want to discuss avenues to improve those decisions, right? The first is seasonality in wind. So in Portland, this is data from Portland Airport site. So in Portland, the wind is majorly northwest direction in summer and east-southeast in winter. You can see that this information is diluted when we consider the whole year wind direction distributions. So first is we consider multiple periods, one for summer and one for winter. And this also provides us with an opportunity to relocate some of these facilities between the time periods to maybe better serve the service area. The second one is considering estimation error in the failure probabilities. So now we assume that failure probabilities lie in this interval rather than assuming it's equal to the weighted average. Right? We capture this using a robust optimization framework, where we basically overestimate the failure probabilities in a systematic manner so that we can hedge our decisions against uncertainty. Right? So now we can develop 3 new models, one which considers seasonality only on top of the SPD model, which you call multi-period deterministic model, considering uncertainty only, and considering both seasonality and uncertainty effects. Right. So this is the case study that we have. We want to deploy AED-enabled drones in a service area to combat out-of-hospital cardiac events. We have 122 demand locations, which represent the zip code centroids in Portland metro area. We have 104 potential facility locations where these drones can be placed. We consider that the coverage importance metric right now is just normalized population, but as I mentioned earlier, it can be a composite metric which considers different factors, right? And we study this for 2 service standards. One is providing 90% reliability in 4 minutes, and second is providing 95% reliability in 10 minutes to just see how much that accessibility radius affects decisions. Okay. So the first thing that we wanted to investigate is how much is the model sensitive to this detailed data, right? So the figures on this left, we see that B is the maximum amount of relocations that can happen. We see pretty significant amount of relocation is happening between 2 periods. So that is helpful, right? And the second is they are also sensitive to the wind directions. So in summer, the wind is blowing in primarily northwest direction, right? So this would make deliveries towards the western region or to the west of the facility easier than the east. So therefore, the facilities which are open in summer only should be skewed a bit towards eastern region, right? And similarly for wind, where winds are primarily flowing in the east-southeast, we will have facilities which are skewed towards the western part of the region so that they can deliver in east-based directions easily. And this is what we also see in our decisions. So yes, the model is sensitive to this data. On this slide, we try to answer the question if enhancements in the model, is it actually beneficial, and by visualizing the decisions. So when we don't consider any effect of seasonality and uncertainty, we see these orange points are basically demand points which were promised reliable coverage, right? But in simulations, we see that not all of them are being reliably covered, right? Only a fraction of them are being covered. But capturing those seasonality and uncertainty effects, we see we improve that a lot. Not completely, but to a large extent, we can improve that. Analytically, empirically, we found that this improvement in simulated coverage was 0.57 times higher. So that is about increment by 57%. So on the previous slide, we saw, that there was a gap between what was promised by the model and what was realized in the real life scenarios which were modeled in simulation. Basically, what our goal is we want to minimize the gap between what the average simulated coverage and the model coverage to be as close to 0 as possible, or the ratio to be as close to 1 as possible. So one of the ways to do that is by increasing the number of facilities, right? As we employ more drones in the area, the probability of, basically more drones are available in that accessibility radius, and therefore, the probability of failure would reduce, and we improve this ratio. The other way is by increasing conservatism. So by being more pessimistic about, this is going to fail, assuming worst case scenarios, right? So as you do that, we are actually consolidating facilities towards the urban core in our region. And as we do that, more facilities are available in that accessibility radius, and therefore the reliability is improved, right? So these are two different mechanisms that needs to be balanced. So as we increase the number of facility, we are actually providing more coverage, right? But if we have a certain number of facilities and when we are increasing conservatism, what is happening is we are reducing model coverage, right, significantly in certain extent. So we are reducing that and thereby improving this ratio. So they need to be balanced when we consider practical scenarios. Additionally, we see that when these travel time thresholds are small, that is 4 minutes, our multi-period robust model that considers both the seasonality effects and uncertainty effects is strictly better, right? And for SS2, however, we see that seasonality effects need not be considered because SPR and MPR are pretty close together, right? So if the travel times are long, we can forego maybe considering the seasonality effects, but it is important when you need to quickly deliver it to improve reliability decisions. So like in recap, we see we have modeled this problem and capturing both seasonality and uncertainty improves the simulated coverage values by 0.57 times. And capturing both seasonality and uncertainty is required for when travel time thresholds are small, but just capturing uncertainty is enough for when travel time thresholds are longer. Okay, that's all I have for you guys today. Thank you.
Thank you, Darshan. Really interesting. And if people have questions, put them in the Q&A box, and I have one to start as I'm thinking about this. And you may have mentioned this, but I don't remember. Do you have to also take into account like how frequently these drones are being called out? Because if one of them is off, leaves from their spot and is responded over here, then it's not available to respond. And so is that built in? And then it seems like you have to make assumptions for how long do they spend and come back. And
yes, you are correct, Dr. Dill. We need to take those considerations into account, but currently we have not. So currently we have modeled a static problem when we are not considering stochasticity in requests, right?
Yeah.
When we consider stochasticity, those congestion effects will come into picture, and we need to think about these things. So this was basically an initial attempt, and we need to improve this by considering congestion effects is one, and the other one is we saw that there is still gap between the model coverage and the simulated coverage. So the other way is tackling that assumption about independence and probability. So basically what we are doing is, if this is a demand point and two of them are coming together, we are assuming the failure probability of this is independent of them. But wind directions, based on wind, there is some correlation between them. So we need to capture that correlation to make much more better decisions.
Sure. I mean, it gets complex. I realize when you start out with a question like this, you
Mhm.
start simple and then you
Yes.
you get that right, and then you keep building in more complexity.
Mhm.
I want to back up a little bit to, and to what extent, I'm not sure if you can answer this, but what types of emergencies, like what is on this drone? How is whatever is on the drone when it arrives at the emergency? What are some
Okay.
examples of how it is able to respond to the emergency?
Okay. So basically, this is how in my head an event would happen, right? There is someone who had a cardiac event and someone calls 911. So as soon as that 911 call is placed, these drones are deployed, to that location. Nowadays, the state-of-the-art AEDs are, very technically advanced, right?
Okay.
They are defibrillators. So the state-of-the-art, they give you simple and precise instructions, like vocally, to a person, and a medic need not be there. A regular person can administer this, and they just have to put an AED in the location, and then the AED takes over. You don't need to charge and actually pass the electricity to the patient in this case. So we would have those state-of-the-art AEDs, attached to these drones, and they would be delivered.
Okay. Okay.
Yeah.
I could also, obviously your analysis could apply to all sorts of other
Yes.
types of emergencies and delivering things.
Yes.
But the basics of needing to understand all these constraints, the wind
Yes.
and seasonality would apply, though I guess, yeah, okay. I could keep going on and thinking of other things to consider.
Yeah. So this model is actually general enough to be applied to ground vehicles as well, right? So in ambulance, the uncertainty arises from congestion issues.
Yeah.
Right. So there is travel time variability because of congestion, and in that, multiple periods could represent, morning peak hours, non-peak hours, and evening peak hours, right? There could be those three periods during a daily variation where the locations can change and things like that. And there is still uncertainty that needs to be tackled. So this is a general framework that can also be applied to, other emergency scenarios too.
Yeah, and then I think another important point that was built into it in terms of the locations that the drones would be going to, you explained that you could build in some characteristics of the people, in that area. So I am assuming, for example, in this is that if you have a zip code or an area or whatever, that the demographics are such that they are higher likelihood of experiencing in your example, cardiac arrest, but then you can weight that differently and
exactly.
plan for that. And so when I heard you talk about that, I started imagining particularly residences with a high number of older adults, for example.
Yes, exactly.
And so concentrations of certain types of populations. So,
and we can also go finer. Like I have taken zip code, but you could do it at maybe a census block level, right? Or a block group level, which could be like more detailed kind of thing. Also, just I want to plug in for the audiences. I have some supplementary material to this slide, which includes the multi-period formulation if someone is interested, and some additional results regarding how much time is it taking, and the actual improvements that we are getting. So, and the wind speed and distribution data is also available openly. So yeah, I think you can see this information when the slides are distributed by Trick.
Yes, that is wonderful. So we will be posting the slides. So everyone watching and other people who watch this later will have access to them, and also the links that were in your slides, and the same with Sangwan's. So unless there are any other questions that come through, or if either of our speakers has anything additional that they want to add that they thought of later, and I know that often happens, I can give you that opportunity. But otherwise, I am going, Darshan, do you have?
No, I don't
Okay.
have anything.
Sorry.
Thank you.
I am going to share my screen again to wrap up today's seminar. And I really appreciate hearing from both of you and the research that you're doing here at PSU. It is always quite impressive to hear from our students. So thank you for spending the time. And I just want to remind everyone that after the seminar ends, you're going to have an opportunity to just do a brief survey for us that we always appreciate getting your feedback. And if you have not already, sign up for our newsletters so you can hear more about our events. And again, I want to thank Darshan and Sangwan for the work that you've done and sharing it with us today. So thank you. And that's the end.
Thank you for having us. Yeah.
Thank you so much.
All right. Thank you, everyone who attended.